the new mandate that the executive order that I was discussing last time.
Cryptic, cryptic friends, whatever.
So here now probably this executive order is saying that like the crypto officer who will be appointed, you should have a background in either in mathematics or in engineering.
So that is for every organization. Mostly,
If he should understand the cryptography, otherwise you cannot appoint somebody with a crypto.
Yes, for like internet, for cheap, AWS for cloud. That's a crypto. That's a company.
We have a lot of crypto architects.
ऐसी कोई कंपनी है जो स्पेसिफिकली इसको
जितना सारा ब्लॉकचेन कंपनी है उन लोगों को क्रिप्टो में ही काम है. इतना सारा स्टार्टअप जो है, so
certifications are required.
that I can comment, I can speculate.
Any kind of certifications in cryptography?
I think SANS has a certification. SANS and crypto council is there, but those are mainly for the mathematicians, not for the engineers. We just need to understand what is happening. But cryptanalysis can be done by mathematicians. We really cannot, we can, but that is a full-time job. And
So we are mainly concerned for SSL,
but crypto has lot of like for hardware industry, crypto is more like crypto is really has a very big impact on the hardware industry. Let's see that because nowadays cryptography we really do not care about the software level cryptography. We usually go to the hardware level. Now let's come to this. Okay, this is another level of cipher that was used in during the World War. What is this? The same mechanical thing. It's just a manual. Like it looks simpler. C means these numbers, right? You know how to rotate these. These are the dials. These are the password. 1, 2, 3, 4. These 4 rotors are kind of the password. You just set this thing, and now for every letter you will have a number. You just send this number. Now the moment you are done sending the message, change this rotor position. So the new number now C is represented by 26, 44, 64, 79. The moment you change this rotor position, these numbers will be changed. Right. So this was another simpler but very famous and very effective communication, and the communication used to look like this. January 1917, the World War I was running. So you just see, this is the message sent. People can decipher only if they know that these rotor positions.
But how the other party used to initialize at the same time?
There is a pattern. How to set that? That pattern was known to them. Just the similar thing it used to happen in this Enigma machine as well. Enigma machine, how they used to set the pattern? The trick was every morning German radio used to broadcast the weather report. In that weather report, they actually said that this is like if the 4th letter is like this, or if the 7th word is like this, then this will be like there is a function. That function is known only to those soldiers, and it is every day it is changing. But that function is coded in that weather report. So that's why it was very difficult for them to understand, because they started thinking that what is the one thing that every day the Germans do, so that all the soldiers in the morning can know that position, total position. What is the thing? Then it came to their mind, okay, the weather report that the German radio is sending every day. So this is clear how that cryptography used to happen in those days. And if I just Yeah, but the German, that was, I think Germans were there for, it was the colony of German, some of the. What are these ladies doing? What is the name of this job role? Anybody can guess? During the First World War and Second World War.
Mosque.
Okay. What these ladies are doing? What is the job role? What is the name of this job role? Anybody? So every day, the lot of messages were intercepted. Not all the messages were encrypted using this Lorentz machine or Enigma machine. And not every time it is the only not the German message, but also there are other like Japan and other nations. So they used to intercept all these messages, and they used to find out that what is the actual message. So the mathematicians, these guys are not mathematicians. Mathematicians were there. They used to say, okay, this is how you can decipher this thing. The formula they have given. These ladies, that time there is no computer, there is no calculator. These ladies used to do that sound. Decryptors. Decryptors, yes, actually, but they had a better name. That time, they had a better name. Do you know what is that? They are called computers. Yes, that time, computer was not there. It is long back before the people thought about a computer. This job role was computer. In fact, I had that thing, but probably here it is not there. You can search. In fact, we want some computers. There is a advertisement in some English newspaper. Computers required. Ladies can apply something because men went to the war. They are fighting. Yeah, men are fighting. So the ladies can also contribute. So they are appointed in those roles, and they are called computers. In fact, today we are calling the same thing as computer because actually this thing came to do the same thing, to decipher the message. So that's why that time these human computers were replaced by what is created by Alan Turing, and that's why they are called, they used to call it computer. Same thing, computer, that is a human computer, there is a machine. Okay, so that's how this word computer came. They are called.
The only thing is now we have to
Oh, how did you know?
Same clothes.
Or they went to shopping together. Okay. And what else is this? Okay, this is the same thing, this right, and this is the scissor cipher. A is replaced by C, T is replaced by D, and this is the substitution cipher. Okay, fine. Now let us come to that. This is just some fun facts I will. Not case study, just some fun facts I wanted to share here. We had nothing to know do with the human computers, but that is how the computer came, and that's just the way we are discussing. Okay. So encryption function. Now we need to know what is an encryption function. Here also Shannon has given a very nice description that when an encryption function, what function we can call up encryption function? What will be the property of an encryption function? In such a way, if there are two different numbers, x1 and x2, any two numbers, just take any two numbers. If you apply the encryption function, ek means with respect to k, like one single key. With the same key, if you apply the same encryption function, if they have same ciphertext, that means the plaintext are same. Right? Two different plaintext, apply the same encryption function with the same key. If they will produce the same ciphertext. And also the reverse is also true. If you take two ciphertexts which are identical, and if you decipher them with the same key and the same description function, they will give you the same plaintext. That is property number one. In mathematics, we call it an injective functions. Right? If you remember your school days mathematics, there are something called injective, subjective, objective. There, it's one-to-one method to say that. Okay. And why it is required? Because The simple thing, Bob gets a ciphertext and then he decipher it, decrypt it. He will not know which one, whether X is the message or like X1 is the message or X2 is the message, because they will produce the same ciphertext. So this will not work, right? Fine. So far. And if plain text equals to the ciphertext, the encryption function is a permutation. That means C is a rearrangement of P. Here we have C plain text is A to Z star, C is also A to Z star. That means if we have make a permutation, we will not create something new. Like if it is A to Z, the ciphertext will also belong to A to Z. If it is a number say 0 to 256, then the plain text and ciphertext both will follow the same thing, right? This is what he said. Now also it comes to one more thing. Plain text and this ciphertext will have the same length also, and the length would be fixed, should be. Here, if we do the plain text, it is a like P and C will have the same length. Then only this permutation will work. Otherwise, it will not happen. Okay. Now we have done some basic maths. Not actually, we have done a little bit of history and theory. We have covered the theory. Now let us come to the basic maths. And before the lunch, we'll just come into the cipher and then we'll have the lunch. Then we'll see what is DES, AES and all. So usually if you start any other cryptography book and all, if you start reading from that, probably it will start from the AES and DES, but these are the background that we should know to understand what is AES or DES, right? Otherwise, there will be just some new terminologies. Okay. Now let us mathematics. I'm not taking much time here. We all know what is binary. We all know what is decimal. We all know what is hexadecimal, right? So here, why I have given this picture? Odometer. Okay. So probably we all know what is decimal number system is. I'm just making a quick refresh. This is a decimal number system. This rotor has 10 different values: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It starts rotating 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it rotates further, it becomes 1. Then all these two rotating, 9, 9. Then it changes. So this is the decimal number system, because each rotor has 10 different values, 0 to 9. Simple. And this is the number system. So if you remember in our primary school, probably there is a number given and we used to write 1 into 1000 plus 2 into 100 plus 3 into 10 plus 4. Remember, we used to do that, and then like this ones, tens, hundred, thousands. 1, 2, 3, 4 means 4 is the ones place, this is tens place, this is hundred place, this is thousands place. We used to do that, remember?
It is 800.
So, sorry?
Unit 1000.
Yes, unit 10, 100, 1000. And when 1, 2, 3, 4 means whatever is in the unit place, that is 1. When it is tens place, it is 10, 100, 1000. That's how we used to do. There are 10 different values in the rotor. Now think there is a rotor which has two values, 0 and 1. 0, 1, then again it becomes 0, it becomes 1. Then again 0, 0, 0, 1, 1, 1, then it becomes 1. Right? So any number system you can think of as an odometer. Any number system. And here it is 1 means 0 power, so 10 power 0, 10 power 1, 10 power 2, 10 power 3, even after that 10 power 4, 10 power 5 and so on. So any number you just place 7, 8, 9, 1, 2, that means 7 into this number, 8 into this, 7 into 10 power 4, 8 into 10 power 3, 9 into 10 power 2, 1 into 10 power 1, 2 into 10 power 3. That's how the number is formed. We do the same thing for binary. Probably you know that in binary we do that, but I do not know whether you have connected the this like you have linked this connection with the decimal number system. In the decimal number system also we do the same thing. But in the binary we all know that it is 2 power 0, 2 power 1, 2 power 2, 2 power 4, and just give any number like 1012. That was at 1011. That means 1 into 2 power 0. That means 1 into 1 plus 1 into 2 plus 1 into 4. 2 power 2 is 4 plus 1. I think it is 0. This is 0. And now this was 1 into 8. So whatever is the number, right?
Yes.
Sorry?
It was 300.
Hmm?
0, 1, 2, 3.
Sorry?
Hexadecimal will be 2 to the power of 2 is one.
Oh, sorry. This one, right? Here I have written it. So this is 11, right? This is 11. Okay, fine. Now how to do the reverse? We can do the same thing. Actually, this is a very nice thing to do. Let us write 1, 2, 4, 8. Give me any number between 1 to 15, 0 to 50, any number, somebody? 6. Okay, 6. 6 means we'll just try to figure out which 2 we can add and make 6. 4 and 2 is 6.
0, 1, 1.
And 14 somebody said. Which of these numbers if we add becomes 14? This and this. 14 means it is E, right? In hexadecimal we call it. So now this is binary. Hexadecimal is very much similar to decimal, but it has 16 numbers. So 1 to 9, then 10 is called A, 11 B, 12 C, 13 B, 14 E, 15 A. Right? Quick refresh, fine, no problem. Why hexadecimal is so popular? It's very simple. Just take any hexadecimal number, you can actually convert into 4 bit of data. Every hexadecimal, because 2 power 4 is 16, that's why any hexadecimal number, if you convert, it will be a 8-bit binary data, 4-bit binary data. Fine? Now, and that's why we usually write it in hexadecimal, so that binary is a very long one. Instead of writing 4-bit, you can write one single letter. That's why we usually use hexadecimal. Fine, now let's go to the next one. What is encoding? Why do we need encoding? First of all, why do we need encoding? Because
to easily identify or
oh, I'm telling you. There are all these binary data. It is being sent from the one computer to another computer. It can be sent as a printed form. This is for me, for a human being, it is a long data, right? And secondly, how we can represent these data. We understand A to Z, like we have A to Z, all these 26 alphabets. We know some other actually once upon a time everything used to be printed. Now all the binary, like if we just print all these 010101, it will be a very big thing, and it doesn't make much sense also. That's why we always try to convert this binary data into something printable format. So we had one nice printable thing called ASCII, right? That's how we can represent, just for representation purpose. Because 0101, this format is very difficult to handle, even for the software also. Because when we are opening a file, it might open it as a text. Binary opening, you have to give a separate, like whatever language you are using. If you want to open it in the binary form, you have to give a separate flag for that. By default, always every computer software understands text. The printer understands text. Humans are much more comfortable with the text. So we really, and more than that, When we are using HTTP, HTML, there is nothing in the HTML, there is nothing called binary, right? So in HTML, we have to convert them into some printable format. And HTML understands ASCII. When you are sending a mail, it's not a, I should not send, if I send you a mail with all zeros and one, who is going to read that? We have to convert it into text. So that's why all these data, all this binary data, we take 7 bit of them, 64 bit of them, 6 bit. 60, base 64 encoding means every 6 bit for like, it is an endless string of 0, 1. Whatever. So now I will just take 6 of them. It will correspond to an ASCII value, right? ASCII is from 128 bit, right? It is 2 power 7. But okay, so we could have taken, but why 7? Why not 8? Why ASCII has only 7 bit? We usually take all the registers and everything is 8 bit, right? 1 byte. But for ASCII,
ASCII is 8 bit, we have 2 to the power 7 is usually 2 to the power 0 calculated.
2 power 7 is 128, is not it?
2 to the power 7 is also 8. Starting from 2 to the power 0.
Yes.
So the 8 bit will come. So coming from 0.
Here
from 0.
We have 16 number.
So sir, 2 to the power 7 is equal to 128.
Yes.
Okay. So we'll be starting from 2 to the power 0.
Okay. Let us focus on say 4 bit of data. 4 bit of data is 16. Total 16.
So it's 15.
No, 0 to 15. 0 to 15. Total 16 data is there.
Okay.
That means this is 2 power 3. Here is 2 power 4. 2 power 4 number is the total number. So since we are starting from 0 to 2 power 3 are total 16 numbers. Similarly here 0 to like 2 power 0 to 2 power 7 we have total 1 to like 2 power 8 like 128 total 28 combinations.
Value is 128. I'm sorry, the value is 128. But itself the value starts from 8 bit now. 0, you will calculate from 0, right?
Yes,
2 to the power
0
0 till 2 to the power 7.
These are 8 bit, yes.
Yeah, it's 8 bit.
Yes. So if it is 8 bit, that is 256. The total combination will come 256.
Then we will not call it as 8 bit number.
Yes, we cannot call it. It is 256. Sorry. And if 2 power 0 to 2 power 6, this is 128. Because 128 is 2 power 7. This is 2 power 8. So from 0 to 7, how many bits? 8 bits. That means 2 power 8 is 256. 8 bit, total 8 bits are there. That means 2 power 8. Here we have total 7 bits.
Say 2 to the power 8 is possible. All bits are raised as 1. We will be having value of only 255, not 256. In binary format.
0 is there, right? 0 is also there.
255.
Highest value is 255, but the total numbers, how many total numbers are there? You got it? I'm not talking about the maximum value that we can achieve. I'm telling how many total numbers are there. So if we have 4 bit, that means the total number we have is 60.
2 raised to 4.
2 raised to 4. That means what is the last? Yes. Because actually we will end here. After that it will be, the next one will be like 1 0 0 0 0. This one. Since we are starting from 0, so this like it will be 2 power 4. Is it fine now? Okay. So I am telling that for ASCII, we all know there are 128 ASCII characters. That means 2 power 7. That right? 2 power 7. But 1 byte is 8 bit. So it should be 256. But instead of 256, why we are compromising 1 bit? We are not getting it.
ASCII is 8 bit or a 7
bit.
Then 2 raised to 7.
Because 1 bit is reserved for parity. Okay. Only 1 bit for parity. So if you leave 1 bit, that means 128 bit is. Now here we are. Yeah. Yes, sure.
ASCII is 7 bit or 8 bit?
ASCII, when you are sending the ASCII character, it is 8 bit. 1 bit for parity. Rest 7 bits are for the printing that number. Okay, so in the if you just open a ASCII table, you will see 128 values total, right? And now we have Unicode, we have UTF-8 that has like 16 bit of data, so 2 power 15 of total. Okay, now here when we are doing encoding, we are using 6 bit, not even 7. Now we are again reducing 1 bit. Again 6 bit, so it will some ASCII character, some printable character. I don't know what would it be. Let us assume like this is colon, maybe this one is A, whatever. So some printable format we will get. If we just get this printable format, it is easy for me to send that communication. It is easy for a machine to get that. It is easy for the machine to print it on the screen as well. Because at the end of the day, either we will print it on that's the question. Why to 6 bit? Why not to 56 bit?
You should take 7 or 8.
Mhm. 8 we cannot take because ASCII doesn't have so many values. ASCII has only 128 bit.
1 is for parity.
So 1 is for parity. Here, so we could have taken 7 instead of base 64. This is called base 64 encoding. Base 64 encoding means all the binary data is converted into some text format. If you open up any certificate, if you just right click and open it in a notepad, it will be just some text, right? But actually it is a binary value. So what it does, it actually encode it using base 64. This is not encryption. There is no key, nothing. This is just something to represent the data. Now the question is why it is 6? Because all the ASCII character is not printable. There are white spaces. LA, there is null character. All these things has a different meaning for the computer and the printer. So we have to leave those things. So that's why only 64 printable characters we have taken, and these are those 64 characters. So anywhere it gets 00, like here I am 01011. Oh, where it is 010111. This one is actually X. This one is actually X. This one 011001. 011.
But this is half of the table.
Why?
63 numbers only.
Starting from 0 to 63, 64.
64 only.
Yes.
But it is 128.
No, not 128 because rest of the characters are not printable. We have taken some, actually 6 bit we have taken, not 7 bit. 6 bit means 64. Total 64 numbers. You can see.
Non-printable in the sense from binary to
A null character, how can you print that? You cannot print a null character, right? So that in the text pad, if you open, that means it is it is the end of the string. So it has a different meaning. Maybe LA /n. /n means it is a new line. So that is not a printable one. But I want a printable text. That's why we have taken 64 data. These are printable actually. Got it? There are more printable. Actually, I think 84 or 85 are printable, but 64 works for me, right? If I just take. So everything we will take as a 64 6 bit of data. Every 6 bit of binary data take and put it like print the character first.
For this will also the parity.
I don't know. We don't need parity for this.
decoding will work.
But
Of course, any just open any base 64. Okay, let me open some.
we still have.
I'm showing you. So this is what this is Microsoft. Okay, I am opening. It's
Base 64 should be some
copy to file. This is a certificate. Okay, I'm just paste. Save. Oh, I'm not. Control. You're getting it right. So what I did here, I just went to the. What I did here. This was I was trying to install these Teams and all. So I'm just opening something. Correction is secure. Here is the certificate. We'll go in detail into these certificates and how it works in the next day's class. So in the, where is my desktop? Here's the desktop. Export was successful. Now I have a certificate. If I open it with Notepad, show more options, edit with Notepad++. Okay, you see these characters, like it is not a printable format. You can clearly see this is not a printable one. These black ones are actually having a different meaning. So if I just do that, this is a ANSI format. I can convert it into something else, but this is actually a binary file. Binary file used to look like this. Now I am doing one more thing. Again, I am doing a copy to file. Next, you see the second option here. Do you read? This is the DCR format. Now this is the same CER, but base 64 encoded. The same thing. And I am finish. Okay. Okay. This one I am again opening. Show more options. Now see this looks something different, right? So this is the base 64 encoding. The previous one is actually the binary data. I forced my Notepad++ to represent it as a text, but all the text it doesn't understand. That's why these BAs, DLE, some nonsense it is printing. But base 64 is based for our result, because either we want to print it on a paper or we want to print it on the screen, right? Or we want to send it. So it's better to send it as a text. If we want to mail it, we can just send it as a text. Somebody can copy and paste and use the certificate. So 01, dealing with zeros and 1 is difficult, because not every byte will have a printable form, will have a printable value. But that's why we are converting it into ASCII. That's why this base 64 is very important. When we are dealing with cryptography and all, when we are using OpenSSL or whatever, this base 64, because we might think that okay, the certificate should be a binary thing. Why the hell this is looking like this? What's the meaning of this? So this is the base 64 encoded. Any binary value we can encode in base 64. And how we can encode? I just showed that one here. This is the table, and from this table we can encode it. Yes. Okay, this one, if I can convert it, I think I can view it as do you see anything like a hexadecimal, encoding hexadecimal, convert to NC? ASCII to hex. Yes, or we can run it here only, I think. Converter, ASCII to hex. It's not showing that. How can I? Okay, I can do one thing. I can open it in the hexadecimal format if you want. HXT is there. Open desktop test, right? This one. The first one is like first byte word 3082. You see, this is the 3082. And if I just open that, this one in Notepad, show more options, edited Notepad. First one is aim. Aim means first character is aim, right? First 6 bit is M. M means what? 0 1 0 0 1 1 0 0. See this one, right? Now see, probably we'll get the same bit pattern here. Oh, this is in hex and 001100, the first 6 bit. Yes, if you have proper like for that you need to have install proper software. Like you to open a bitmap file, you need to have a paint or some picture viewer. You cannot open it in the text pad, right? You cannot do that.
So we are trying to open a .cer file.
Yes, either you use OpenSSL so that you can get the meaning in the terminal, or Windows also has, like if I just open this one, see, now you can see this is meaningful. The Windows, this is coming from the Windows. Okay, it is a built-in tool, or with OpenSSL you can do. But I'm opening it in Notepad. Right? In Notepad you cannot. If you open, of course, you will just see what is. That's what I was. Okay. Now where was I? Fine. Encoding is clear. Why we need encoding? That's why all the cryptographic tools you use, you will get this kind of encoded version. Okay. Good. We know mathematical functions. What is the mathematical function? Everybody has remembered. Mathematical function. Actually, this is the mapping between two sets. XOR. Do we remember what XOR is?
Very famous function.
Why?
BA. Symmetric encryption mostly.
Okay. What is the truth table for XOR? Let us write the truth table. No, you don't think right. 0 0 0 1 up. Is better now? Here I am typing 1 0 1 0 1 1. Okay. Y and XOR A and B. I guess that is better. Is A. Now tell me, what is A XOR B?
0
0. This is
1
1.
1 0.
Okay. So easiest way to remember it, it is exclusive OR. That means if these two are different, then the answer is 1. If they are same, the answer is 0. That's what the exclusive OR means, right? Exclusive OR means they have to be separate. That's why exclusive OR. So if they are exclusive, 0 and 1 or 1 and 0, that is the only two ways. Oh, these are different, right? So that's why these two cases it is 1, and when it is 0, like 0 0 and 1 1 are the same. These two are same. That means that it is 0. Fine, simple, easy to remember. No. Okay. Now let us do one thing. Give me a number between 0 to 15. Anybody? 15. 1 5. 13. And how can I increase the size? 4. Okay. 13. 13 means what? No, A, B, C, D. 13 means D, right? And another number, another hexadecimal number. Sorry, 15. Okay, 15 is there. Another, give me another hexadecimal number. 7. Just below 10. 9. Okay, 9. Fine. Okay, so this is D and F. If I write it in a hexadecimal format. If I write in a hexadecimal format, DF. Okay, again. Oh. If I write it here, DF is a number, another number is 9. So DF, why I take two hexadecimal number? Because like I want a 16-bit number, that's why. D is what? Tell me. D is 13. 13 means 1101. Then F, we usually write, this is a convention, 0x, if we put 0x before the number, that means it is a hexadecimal number, just to denote that this is not a decimal one, a hexadecimal. Okay. And 9, what would be the value? 1. Now from this one, actually it is easy to quickly convert, right? Perfect. Now let us do one thing. XOR. What will be the result? Okay. Okay. Now I am just repeating the same thing. 1001. What will be the again XOR? Just so I have XOR this number D and 9, and now I am doing F and 9. F and 9 I am XORing. What would be the one?
0, 1, 1, 0, 1.
Now tell me. So this is a number. This is a number. This is another number. And this is the result. I'm not talking about ciphertext yet. Don't run faster than the train runs. Okay. So this is, now tell me one thing. Without knowing this one, can we guess this number from this number? Is there any way? Just think about this bit 0. 0 means these two combination might be 1 1 or 0 0. I really do not know. We really cannot find, other than knowing both the number, I really cannot find this one from this number. I really cannot find these two numbers because there are lot of possibilities. For every bit there are two possibilities. 8 bits means 2 power 8 possibilities. Now with 64, that is 2 power 64 different possibilities. I really do not know which bit will be right. So this is something what we call XOR. Guys online, you're fine with this, right? So far?
Yes.
Yes, yes. Please let me know if you like if you need me to repeat something, or if you are not catching something, please let me know. Okay. Okay. Now we know what is XOR. Now modulo. What is modulo? Nothing. Just reminder. Again, I am coming to this. We have something called divisor. Then I want to make it bigger. divisor dividend and what do you call it, remainder, right? Remainder. Fine. So all of us know this thing. You guys used to use this notation or something like this?
Same, same.
Okay. In our childhood, we used to this one. Maybe like. Okay. So you are from not next generation. You are from state board. Okay. Okay. In fact, I was in state board in a like Bengali medium school. So I used to like, and I always see that the convent school students used to do that. So that's why. Yeah.
So for me, I studied in government, but I still use.
Okay. Then my assumption was wrong.
Your school is following.
Yes. It is. Okay. So this remainder, any two number, if I take, whatever will be the remainder, we call mod. In C, we used to write x percent y is the remainder. Remember, this is the function we used to use. Like if you want to find a remainder in C, this is the thing. Even for for quotient it is x by y. In fact, I think in Python also the same notation works. Okay, but they have function also, remainder function. Anyway, so this is the thing. We know modulo. We don't have any problem. Now let us again come here. So this is function. This is exert. Remainder, like we use this modulo every day in our life. The clock. Train time is 18. What does that mean? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 6 o'clock. We use this modulo every day in our life when we are working, when we are looking at the clock. Clock is not. So this is, you can think, this is actually a device which is making us 12 modulo. If we take any number, it will give me 12 modulo. Right? Just take any number, even if it is 100. Keep on counting 100 wherever you end. That is the 112, 100 mod 12. Fine. You probably never thought that this is also a way we can think about modulo or remainder. But this is what we always use. Okay. Now we'll see lot of things because modulo and XOR will probably be the next few hours today and next day. Those are the things that but this is very simple, right? There's nothing to forget, nothing to understand, like nothing to be confused. Now let's come to block ciphers. Scissors shift cipher. We started with that, remember? Now we will convert that scissors cipher into a modern outlook. Previous one we know how the primitive people used to do. Now with our mathematical skill, now we have understood the mathematics behind it. Now we are kind of mathematicians. Now we will try to figure out how this thing we can convert this thing into a proper crypto system, modern day crypto system. Again, this is actually a modulo arithmetic. Like if the key is 2, like take any of the number D, 2 means 1, 2. The next one, fine. If it is 7, take any letter, 1, 2, 3, 4, 5, 6, 7. This is the number, right? Simple. Take 100. Now we are just extrapolating that. Now we are making it little bit tougher. Now let us think. Yeah, sure. So you remember scissor cipher. say the key is -2. That means whatever comes minus 2 times before E, that will be number. That will how we'll encrypt the message. Substitute E with B. That's how. B we will substitute with Z. Right? That's how we do. That's what Caesar said. We can think with a different approach with a modular arithmetic. How? We can just modular arithmetic. We have we know this is a device to calculate a modular arithmetic. Now say E -2, 1, 2. This is C. Any other number you take N -2, 12, 11. It will be L. -2. Now the key might be 4, 5, 6, 7, 26. Fine. Now we are making it a little bit tougher. We are saying no, it is not only 26. The key size may be anything infinite. Then also this modular arithmetic thing work. Even if it is 100, we'll just from A we'll just keep on counting. Whenever 100 ends, whatever is the number, that will be my replace substitute. So this is also using a modular arithmetic. We did not know that, we did not understand. Probably Caesar did not understand himself. But this is actually a modular arithmetic is happening here. Because this is so obvious to us, we never understood that what is happening in the mathematics. Okay. Also, it is now we can make further tough. Instead of A, B, C, D, E, F or the alphabets, we can actually use numbers 0 to 26. These numbers we can take. So it will be much more better. Like instead of A, B, C, D, we can just think of these numbers. Any number take, add the number, make the modulo, represent. It will be better now. So this is what the shift cipher is. Okay. Now tell me, okay, I'm not coming to this. I am using this one again. So tell me, what will be the crypto system would look like? Crypto system is this one. P, C, K, E, D. Now what will be P? What will be plain text? It will be a number from 0 to 25. This is the set. What will be C?
That's what I'm saying.
0 to 25. What will be K? It can be any integer. Okay. In any mathematics book or any cryptography book, if you see this one, a Z with a little bit boldness, this means actually this one. Any integer, yes. Any natural integer. What is any integer?
Non-negative or
Any integer. Z is positive. No, Z plus is positive. Only Z is all integer. Any integer, positive. Okay. So any integer we usually represent in mathematics Z. Okay. So K is any integer.
correct?
Now what will be the E?
Again, 0 to 20.
No, it is a function. Now these are the sets. Fine.
Okay.
This is a function.
So,
remember
to function. C.
C
It's like for C is E.
How about this? Is not it the same thing? E is with E. No, E is the encryption function. This is the function. This is the mathematical function. E mod. If it is 3, P is say 7.
K more.
E mod. Is that right?
Correct.
E mod P.
It is 7. 7 more 25. 6 will come 7. 8. K more P.
P plus This is the one. P plus K mod 26. Tell me, fine? P plus K mod 26. इतना शिफ्ट किया k what is the whatever is the value of k उतना शिफ्ट किया, then I am applying mod 26. This is the mod 26 done. You guys understand? For you follow me in the whiteboard, the teams.
Yep.
You can see the whiteboard, right?
Yeah, I can see.
Oh, yes, sir. Now tell me what will be the D? Decryption algorithm. What is the decryption function?
C plus K, minus K plus K, that depends on, you are removing the encryption, right, the cipher key.
C minus K. Or not.
Exactly. So now you guys are also cryptanalyst. You can look at this is the crypto system. We build the crypto system. This is the crypto system. Okay. Now in the cryptography book, you will usually see all these things. This is what is the main. Fine. Okay. Okay. There is in the notation usually we write like this. It is a small p. This is a small k, and here we also write for all p for all k. That means p belongs to this p. Like this is a set, right? So any member of this set we are representing it as small p, and any member of this set we are representing as small p. Did you understand? Sure. Or we say like small p belongs to p. All these notation you will see. That means it is any member of like 0 to 25, any of the number. It is a set. Capital P is a set. Small p belongs to that set. That's how we usually write here. So this is instead of capital P, because it is not a set. We are not applying the thing on the set. That's for the member of the set. That's right. Got it? Got it? Perfect. See, this is the thing. Now we'll do the cryptanalysis of this. So this is the crypto system we have built here.
Instead of K, we should
No, Z is the set, K is a set of all integers. Small k is a member of that set, that is one particular integer. Right?
That particular integer will be a key.
Like now I am doing, I have one key. You are doing the same encryption, you will have a different key. But both of those keys belongs to this k. Because k is number, all possible numbers of keys are k.
Subset of decay, which is any integer from the subset of
Exactly. Any member of that set.
Yeah. Okay.
Yeah, we call it member. Or
Okay.
set means something 1, 2, 3, 4. This is a set. Say this is the k. Fine. Any of these things we are calling a member of this set. So your k, your small k will be k. Kiran is maybe 1. K. Shomo is maybe 2. K. Part maybe 4. Something like that.
Got it.
Got it?
So, yeah.
So that's why like this k is actually not the set. We are not applying the operation on the set, but a member of the set. Got it?
So, this only works on symmetric type, right?
We are right now talking about symmetric because only one k is there. Asymmetric, for asymmetric, this k has two subsets. One is the public key, and there will be a relationship between these two sets. Okay. Now we have built the crypto system. Now we will analyze it. We will get a cryptanalysis. Is it good? No. It is it is good. One of the major property of the crypto system is it should be easy to compute. The encryption and decryption function should be easy. Yes, it is easy to compute. Satisfied. But an attacker who views the cipher text should not get any information about the plain text. That is the Shannon's second one. But this is not satisfied because it is a cyclic pattern. If I can, I get thousands of messages, easily I can find out what is the size of the key because it is a cyclic pattern. right? And maximum it is a 26 gates. The key space is so small, 26. Though we have made it better using modulo and all, but still it's a cyclic thing. We can ultimately with 26 gates we can do. And again, another problem it has, two different key will produce same ciphertext. Like if I take, sorry, say 2 and 28 will produce the same ciphertext, right? 2, 28, 54, exactly. So that's why two different key will, like many, there will be many keys will produce the same ciphertext and the plain text both. So this is clearly not a good cryptographic function. This is not a good crypto system. This is how the cryptanalysis works. Okay. There is one more way where this is kind of how exactly the cryptanalysis, probably the most popular tool for cryptanalysis is the frequency analysis. What is that? So we just make a ciphertext of all a very large number of text, very big text. What will happen? We know in English the letters how they are distributed. Mostly in an English, if it is a very big text, E will appear most of the time. Right. Now, from that ciphertext, easily will find what is the number which is appearing most of the time, what is the letter which is appearing most of the time. You can first guess will be that will be the E. Similarly, T, S, H. If you have played Waddle usually like when we think in the same way. We usually start to find the first word with something with E, T, S. Like my trick is always the first word I try with is Aster. Aster. So all these, yeah, most of the used words, right? So this is a easy way. Like if you do the frequency analysis, even though if you do not have any idea how it is working, whether this is a cyclic pattern or not, you can actually replace the letter. That's why the story I told you about the Lorentz cipher, how exactly they did decipher it, because they got 10,000 different samples. They just learned that frequency analysis and found okay, this is the thing. Right. That's how it works. Got it? So this is a very simple thing, but this is actually the most popular tool used by the people.
What is the random frequency analysis?
Okay. So in the cipher text, what is the letter that is appearing maximum number of times? Maybe say it is P or it is something X. And we know in English, E is the most used letter. In English, if you just take any book or anything, mostly E will appear most of the time because E is the most popular letter. That's why frequency of E is highest. And in my ciphertext, I can see X is used highest number of times. That means I can guess, okay, E and X might have a relation. E are replaced by X, right? What is the second most? That is T. So whatever is the second most used letter in the ciphertext, that might be T. But for that you have to have a very large number of ciphertext. Not one, two single sentences will not work here. But if you have a very large number of ciphertext, you can easily find out what is what. Maybe all the cases will not work, but it will give you some. At least you cannot find E, but you can find T. Now you can find T, then you can find, okay, what are the next thing that might happen. So you can create a pattern, you can correlate that. So this is called frequency analysis. So obviously our Caesar cipher will not survive a frequency analysis. This is the substitution cryptanalysis, as I said. This is the frequency in the ciphertext alphabet and the plain text alphabet. We can just match. E, if there are maximum number of E is probably replaced by U. Okay. Or what we call Chanakya's rule, whatever was Chanakya's cipher. So what is this like? If we do this one, then this is a better cipher than Caesar. This doesn't have a cyclic pattern. Now tell me once again. Let us quickly run the same exercise here. We'll create another P2 system. P is A to Z, right? C is A to Z. There is any P.
Right, so small extent
Yeah, this is fine. Like when you are sending a message in capital font, what does it matter? People are interested about the information, right? Usually, capital letter is used because it is stating the it's a Morse code. Okay, what is the key? Key is that table. This substitution table is the key, right? And E is the table value, like table value of P and table value of C. Okay. So instead of table value, okay. Okay, I'm just quickly reading the substitution table. Okay. Okay, so this is I am just representing this finding the table value as a different function named phi. It's just a function. We can define phi. And but this is also not a very good cipher because the key space is 26. Okay. Now we'll start with or somebody will come us to for
Nobody will. You have to go. Otherwise,
Guys, you ready?
it will be nice.
Okay. Okay. Then we'll do this cipher, and this will actually start the modern day cipher. We'll analyze this one, and then we'll go to one-time pad, which is kind of an unbreakable one. Till date, this is the best cipher, and whatever block cipher, whatever thing we are now implementing, we are implementing on the base of this. That's the real best one. Then we'll go to the AES and DES and start. We'll do the same analysis for AES, DES. In fact, more than that, we can do some interesting thing. We can try to implement a block cipher. We'll do that. Okay. I think 2 o'clock is fine, right? I'll just give you 10 minutes lesser time for the lunch. So there are many things to cover.
You can start at 1.
You guys can hear what Partha is saying? Is it coming from my monitor? Hey, you guys can hear what Partha is saying?
Not audible.
Yeah, Partha is saying that you guys must have had your lunch and are sleeping now. You don't need a lunch break. Anyway, we'll come back at 2 o'clock.
Okay.
Okay, thank you.